squared. So -1 times -1 is 1. But we're going to subtract it, so it's going to be another -1 equals 0. Now we're going to FOIL this out to where we get a polynomial. So we're going to have 4. So first he's FOIL. So we're going to have 4 minus 4 lambda plus lambda squared minus 1 equals 0. And then we're going to combine these coefficients and rewrite them. So now you have lambda squared minus 4 lambda plus 3 equals 0. Now we've boiled this down, all this crap down into a single quadratic equation. This is good news because we know how to solve for the roots of a quadratic equation. We have this equal to 0. It's as simple as plugging in the quadratic formula, which is -b, so it'll be 4 plus or minus the square root of 16 squared, or 16 minus 4ac, so that'll be 12. All over 2a, where a is just equal to 1. So when we do this, it's going to be 2 plus or minus 1/2 of 2, which is going to be 1. So therefore, our eigenvalues are equal to 1 and 3. So, if our eigenvalues are equal to 1 and 3, we can solve for the frequencies of this system, where omega is equal to the square root of our eigenvalues. Therefore, our omega is going to be equal to the square root of k over m and the square root of 3k over m. That's how we solve for the natural frequencies of the system. So to reiterate, what we're going to do is we're going to set up our system as a system of algebraic equations, or ODEs, excuse me, a system of ODEs. We're going to put it into matrix form. We're going to put it into the form of the eigenvalue problem. We're going to take the determinant of that matrix. We're going to get the characteristic polynomial. We're going to take the square root of each of those eigenvalues and then arrive at our natural frequencies. Okay, so now that we found our natural frequencies, that's only half the battle. We need to find these things called the mode shapes. And what the mode shapes do is they sort of describe the relative amplitudes of each of the bodies. If your system has n degrees of freedom, you're going to have n frequencies and n mode shapes. Let me reiterate that in linear algebra terms. If your system has n degrees of freedom, you're going to have n eigenvalues and n eigenvectors. And so V is usually what we use for eigenvectors. So I'm going to write our omega is going to relate to our eigenvalue, and our mode shape, capital X, is going to relate to our eigenvectors. So the formal definition of an eigenvector is going to be a vector that when applied into a coordinate transformation only scales in value, does not change direction. And that's why we can express it as just a constant times that v. So this x right here is actually not just a vector, it's a special type of vector called an eigenvector. And it makes a bit more sense, right? So like if I had a v equals lambda v, we have a matrix times a constant. That means that when applied to this coordinate transformation, it's only scaled by a constant value. Is this making sense?
No.
Okay. That's not so important for this class. For this class, what's important is that our eigenvectors are going to be our mode shapes.
Yeah.
So now, I'm going to erase a lot of this and keep our eigenvalues which again are not our natural frequencies, they're the square of our natural frequencies. And then we're going to keep, oh bummer, right, I remember what I had. Okay, we're good. So we had 2 minus 1 minus 1, 2, x equals 0. This is what we had to begin with, and I had factored out that k over m from before when I gave these definitions. So what we're going to do is, eigenvectors have this neat property where if you multiplied each of the elements in an eigenvector by a constant value, that new vector is also an eigenvalue of the system. So what we're going to instead do is, instead of saying that x is going to be equal to x1 and x2 in a vector like this, what we can do is we can make a normalized eigenvector. So what we're going to do is we're going to instead just declare that x1 is equal to 1, and now x2 is, in terms of these, x2 is going to be equal to x2 divided by x1, and this is just our new x2. So we're going to declare it like this, and now since this is equal to 1, this is our only unknown. And this is good, because that's going to save us like half the trouble of trying to find the components of these eigenvectors. So now what I'm going to do is I'm going to replace x with 1 and x2. 1, x2. Oh right, I have to do the minus lambda, minus lambda. Sorry about that. So once again, this is that combined matrix that we had from before, where we have the eigenvalues inside the matrix. I apologize for that. Okay, so we've got a matrix that's dependent on lambda, and we have a vector dependent on our x2. What we have here is a matrix form of a matrix form of a system of two equations with one unknown, which means that this is absolutely solvable. Therefore, what we're going to do is we're just going to pick one of these rows to solve for x2. And just for convenience, because this first element is going to be 1, I'm going to pick the top row so that I don't have any products of lambda and x2. So I'm going to matrix multiply just the top row, because that's the only one we're going to need to solve it. So I'm going to take these two and put them on top of there. So I have 1 times 2 minus lambda times 1 minus, and then plus a negative 1 times x2, x2 equals 0. So again, you can save yourself the trouble of multiplying this whole matrix out by doing the only row that you're going to need to, like, you only need one equation out of these. So now I'm going to go ahead and solve this. I've got 2 minus lambda is equal to x2. Look at that. We've now determined our x2 in terms of our lambda, and guess what? We already have our lambdas right here. Therefore, our x2 is going to be 1, or our x is going to be 1, and then on the bottom we're going to have 2 minus 1, which is 1, or 2 minus 3, which is negative 1. These are our eigenvectors right here. So instead, let me write this another way. This is saying the exact same thing here, where it's going to be 1, 1, or 1, negative 1. These are our eigenvectors of the system. Now what's crucial to remember is that there's a 1-to-1 ratio with the number of eigenvalues and the number of eigenvectors. And it's also important to remember what solution goes with what value of lambda. And so I'm going to say that this 1 is going to be lambda 1, and this 3 is going to be lambda 2. And in that case, the way you can write that is going to be, this is going to be x parentheses 1, x parentheses 2, just like this. So that way you can keep them consistent. It's good to remember that just to, like in practice. Like in an exam, you'll probably be just asked to solve for all the eigenvalues, solve for the eigenvectors, and then you'll just present them. But it's important for you to just keep which ones go with which consistent.
Those are eigenvectors, correct?
These are eigenvectors, these are our eigenvalues, and then our natural frequencies are going to be the square roots of these.
So the 1, 1, 1, and 1, -1, those aren't eigenvalues within them?
No.
The 1, okay.
So eigenvalues are just a scalar, one
Right.
quantity.
Okay.
Eigenvectors are vectors.
I see.
They just have constants in their elements,
Uh-huh.
but they are vectors themselves.
Okay.
So now what this is going to look like, because we had x1, x2, x1, x2. So when we draw our system again, here's what the mode shapes actually mean. Okay. So when we excite this system and it vibrates, there's two ways it's going to vibrate. The first way is going to correlate to our first eigenmode. And that's going to be, when we push this, they're both going to oscillate just like that. That makes sense. So it's like, in comparison to the amplitude of our M1, our M2 is going to be the same magnitude and same direction. So they're both going to move in exact unison. And this makes sense because all three of the springs have the same K value and these have the same M value. And then the other way is going to be with the opposite direction but the same magnitude, 1, -1. So this is the other eigenvector or mode shape of our system. Does this make sense?
So the values inside the eigenvectors, are those like amplitudes?
Yes. They're the balance of the relative amplitudes of vibration. And so when they're gonna, the reason why it's good to keep which eigenvalues go with which eigenvectors straight is because the mode shape is going to oscillate like this when the frequency is square root of k over m. But they're going to go like this when it's the square root of 3k over m. So they have to be resonating at different, or they're oscillating at different frequencies for each of the mode shapes. They're not the same frequency between this and this. That make sense?
For each frequency, it's one of the corresponding eigenvectors.
Yes. This frequency goes with this eigenvector right here. And then this frequency goes with this eigenvector right here. That makes sense? Any questions before we move on to one more thing about the eigenvalue problem?
So that value inside, is that like also
Which one?
one of these?
Okay.
These values, is
Yeah.
that also magnitude? So if it was like 3, does that mean the amplitude is 3 too?
Since they're normalized eigenvectors, it just means that if you're given the amplitude of m1, for example, it would be the same. And it would be the same but the opposite direction. So they're ratios in comparison to
they're
the
ratios.
M1 because they're normalized. They're not absolute amplitudes.
Okay.
So it's the difference, or it's the quotient of amplitudes, not the exact amplitudes themselves. Does that make sense?
Yeah.
Awesome. Okay. So the important thing to
Why is the K over M within the frequency?
because in that equation I had written before with like the 2 minus lambda, -1 and -1, I had the K and M factored on the outside.
Right, okay.
Because I declared that K1, K2 were equal to
Yeah.
K, M1, M2 were equal to M. Therefore, all the terms had some factor of K over M in them,
Right.
and so I could factor it out for each of the elements.
Okay.
And that's what I did.
Yeah.
So in these, I just factored them back in,
Mhm.
because it's actually going to be K over M, 3K over M for the eigenvalues. Take the square root of each,
That's what we're gonna get. So you should be able to say, okay, well, if Lynn asks you like, all right, you have this system and it has these eigenvalues, and you're given like the M inverse K for matrix, you should be able to tell him how the system is going to respond to that frequency. So it's like he's already given you the eigenvalues, or he's already given you the natural frequencies, and so what you're going to do is you're going to determine the mode shape from that matrix using the form of the eigenvalue problem. And so there was some confusion this week in office hours about the exact form of the eigenvalue problem. And I'm going to show you that there are multiple different ways to say the same thing about the eigenvalue problem. Like they'll yield the same answers, but it's just for computational convenience, there are some forms that are easier to work out than others. Personally, I'm always going to recommend this one right here, which is M inverse K